right, so let's get started. Last class period, you kind of built the whole, spent the whole class period building this equation here. All right, this is going to be a really important equation in this thermodynamics chapter here. We have our delta G, our Gibbs free energy, our delta H, our enthalpy, and delta S, our entropy here. All right. There's like, we're going to try to like boil these three variables down, these three thermodynamic variables down to a key word here. Delta G tells us about the spontaneity of a reaction. All right, and by that I simply mean, does the reaction happen? Which is pretty crazy, that for every chemical reaction we can calculate this quantity, this free energy, and that tells us whether or not that reaction is actually going to occur. Delta H, our enthalpy, this tells us about the heat that is absorbed or released in a reaction. All right. Importantly, why would heat be absorbed or released in a reaction? Like, what's happening? Why do reactions absorb heat? Why do they release heat? All right. What's going on that's causing that heat to be absorbed or released? Does anybody know? What's up? Boom, making and breaking bonds. Exactly, right? Awesome. So all the heat goes into making, or rather breaking bonds, and then we get heat back out when new bonds are formed, right? So yeah, the delta H tells you about how favorable or unfavorable your bond formation is. All right, and then entropy is this weird one. I don't know who could have guessed that this was a key part of whether or not a chemical reaction happens, but whether or not it creates disorder. All right, that's this keyword that I want you to have tied in your mind. And I remember when I was in general chemistry and they were like, oh yeah, delta S is a measure of disorder. And I was like, all right, that sounds like a lie. I'm going to get further on in my chemistry career and I'm going to understand what it really means. No, no, no. To this day, I still thinking about it as a reaction creating disorder. That's literally what it is. For whatever reason, the universe has this energetic push towards a more disordered state. All right? Cool. Remember signs. So delta G, we want our delta G to be negative. That means that the reaction is spontaneous or does occur, right? If a delta G is positive, we would say the reaction is non-spontaneous. All right, which means that it does not occur, at least not in that forward direction. But remember, we've like graduated to the point where we're thinking about reactions going in both directions. So when we say non-spontaneous, that means it's spontaneous, but in the reverse direction. All right. Delta H, what did we call? We got cool words for delta H. What do we call a negative delta H? Exothermic. A reaction that releases heat is what we call exothermic, meaning it releases heat. A positive delta H is an endothermic reaction, which means it absorbs heat. All right, and then delta S, a positive delta S is good, all right? So from the universe's standpoint, a negative delta G is good, a negative delta H is good, but a positive delta S is an entropically favorable reaction. Meaning that it does create disorder. Whereas a negative delta S is an entropically unfavorable reaction. Meaning that it creates order. Okay? The universe loves reactions that create disorder. And that's kind of weird, especially like looking around this room, because human life is indeed very ordered, right? Us as organisms are incredibly ordered beings. All right, this building, very ordered, but there's a lot of work that comes into it, and there's a lot of compensating reactions. We gotta eat, we burn calories, we got a limited lifespan on this earth, right? We are high maintenance individuals because we are so highly ordered, right? So we gotta do all this crap that the universe is gonna be okay with because it is allowing us to like build all that order in ourselves. All right, cool. All right, so how are we going to use these variables here? Last semester, when you talked about thermochemistry, you already had sort of been introduced to this delta H variable before. There's a very important principle called Hess's law that made that thermodynamic variable that much more usable, that much more convenient. All right, Hess's law is when we combine known chemical reactions all right, both the chemical equations and their thermodynamic variables. And we do that in order to study some unknown reaction. And this is true of any known chemical equation. You can always combine them, all right? But there's going to be a handful that are going to be really, really convenient to us. And we'll see why this is in a second. These are what are called formation reactions. All right, a formation reaction. They always look the same. We have some compound as our product. All right, and my reactants are every element in that compound in their standard state. All right, I'm going to leave a little bit of room for one more like rule here, but I'm going to give an example. Okay, so if I take a compound like nitrogen dioxide, all right, that compound is my product in this formation reaction, and my reactants are those two elements, nitrogen and oxygen, in their standard state. So nitrogen is a diatomic gas in its standard state, and oxygen is a diatomic gas in its standard state. All right, so my compound, I just take each one of those elements, boom, in their standard state. But there's a weird thing about formation reactions. All right, our formation chemical equation is we always balance these such that the product coefficient stays as 1. All right, so I'm going to balance this chemical equation in such a way that I keep a 1 out here on the product side, which means we're going to do something we're not usually able to do, which is use fractions to balance my reactant side. All right? So my O2 is fine. I got 2 oxygens over here, 2 oxygens over here, but I only have 1 nitrogen, so I'm going to balance this formation reaction with a 1/2 here. All right, we're going to see why in a second. That makes these very, very convenient reactions. All right, and what we're going to do is use Hess's law here. Okay, actually I lied. First thing we're going to do is I want you to see if you can give me the formation reaction for another one of these compounds, N2O4 gas, dinitrogen tetraoxide. All right, so same two elements. So my nitrogen in its standard state, my oxygen in its standard state. I'm going to keep this a 1 out front of my product side. So I'm going to balance, in this case, I'm going to need 2 of those oxygen gas molecules in order to do it. Okay, so these here are my known reactions. All right, I've already studied these in the lab. I've already went ahead and measured their free energy change, and so I know that the delta G for this reaction is 51.3 kilojoules per mole, and the delta G for this reaction is 99.8 kilojoules per mole. So these are my two known reactions here. All right, so first of all, this first reaction, what would we say given that value of delta G? Is this reaction spontaneous or non-spontaneous? This one would be non-spontaneous. And what about my second one? Also non-spontaneous. Right, because they both have a positive value for delta G. Okay, so these are my known reactions. And what I'm going to do is I'm going to combine these in order to study an unknown reaction. All right, I want to study this unknown reaction. All right, where nitrogen dioxide gas gets converted into dinitrogen tetraoxide. And this reaction I haven't studied before, so my delta G, I don't know. That's what we're trying to figure out here. All right, well, let's be good. We need to balance this chemical equation here. So I'm going to put a 2 out front. Whoops. On my reactant side. Cool. All right, so this is the name of the game. We got two reactions that we've studied before. We know what their delta G is. What we don't know is the delta G of this unknown reaction. And what we're going to do is we're going to combine these two known reactions in such a way that will allow us to figure out what that delta G value is. Okay? All right, so first of all, my product N2O4, my product N2O4, so I'm going to take this reaction as it is. I'm just going to copy and paste it, along with that delta G value as well. All right, but if I just summed up these two reactions as is, that's not going to work, right? I have nitrogen dioxide as a product over here. It's as a reactant over here. So I'm going to have to take this reaction, this chemical equation, and flip it, right? All I'm going to do is put NO2 on my reactant side and these two on my product side, right? Just flip my chemical equation. All right, as we learned early in the semester, we don't have to look at a chemical reaction as just going in one direction. So I can talk about my reverse reaction here. All right, so I had to flip that reaction 2. Let me actually call these reaction 1, reaction 2. And when I flip my reaction, that means I need to flip my delta G as well, as flip the sign of that delta G. So if it's 51.3, positive 51.3 in the forward direction, that means if I'm going in the reverse direction, the delta G would be negative 51.3, right? Remember, non-spontaneous means it's spontaneous in the reverse direction. So now my delta G here is negative 51.3. But if I combined these, I still wouldn't have my net reaction here, because this reaction has 2 NO2s, and I only have one of them over here. I need to get 2 of them. So what I'm going to do is I'm going to take the whole thing, this whole equation here, and I'm going to multiply it by 2, including my delta G as well. So that means, so flip 2 and multiply by 2. So that would give me 2 NO2s. That would give me 2 times 1/2 was just 1 nitrogen gas, and 2 of those O2s. And I'm going to have to double that delta G value as well. So now my delta G is equal to negative 102.6 kilojoules per mole. All right. Just for the sake of cleaning this up, I'm going to rewrite these, copy them down here. All right, when we combine our reactions, when we combine chemical equations, we're going to add these 2 up, right? I'm going to combine all my reactants on my reactant side of my new chemical equation and all my products on my product side of my new chemical equation. Okay, and I'm going to have to write kind of tiny here, so I guess I could just shrink. So these 2 here, plus my next one. All right, so notice that I just combined my reactant side, my reactant side of this equation and my reactant side of this equation. They just got combined into a new chemical equation where they're both on the reactant side. Likewise, I'm going to take all my products and combine them together on the product side of this new chemical equation, right? So this thing here, I'm going to copy that onto my new chemical equation, plus the product side of my second chemical equation. So this is what we mean when we say we sum a chemical equation. I have to shrink it. All right, so first make sure that we could see how I got my new chemical equation. Again, combined all my reactants onto the reactant side of a new chemical equation. Combined all my products onto the product side of a new chemical equation. That's what we mean by sum up reactions. I'm going to get rid of this coloring though because it's going to get real busy. All right, and then what we're going to do is we're going to go through and we're going to get rid of anything that appears on both sides of our reaction. All right, so this reaction says that 2 oxygens were consumed and 2 oxygens were produced. So there's no net change in oxygens. There's no net change in our nitrogens. And so my net reaction when I sum these 2 up is just that reaction that I was trying to study in the first place. Right? That was the goal here. And just like we were able to sum up these 2 chemical equations to get our chemical equation of our unknown reaction, we get to do the same thing with those thermodynamic variables, in this case my delta G. All right, so I'm going to take those 2 delta G values for those reactions and sum them up. And I get a delta G of negative 2.8 kilojoules per mole. So then what would we say about this new reaction that we were just studying here? Would this reaction be spontaneous or non-spontaneous? Spontaneous, right? Because it's got that negative delta G. So we took these 2 reactions that we knew something about, and we used them to figure out a new chemical reaction that we knew nothing about, all right? And we can conclude that this reaction is spontaneous. Okay? Cool. So Hess's law allows us to combine known reactions and their thermodynamic variables to figure out our delta G or any of our thermodynamic variables for this unknown reaction. What's up?
So to get the new delta G, you just combined it.
I just summed these two up. Yep. Just like I summed, and I had to do some work first, right? I had to flip this reaction and stuff like that. But just like I could sum these two up and get my new chemical equation, that means I can sum these delta G's up to get the delta G for that new equation. All right? Cool. So these thermodynamic variables, one of the reasons that they're so powerful, they're so useful, is because they're additive in this way. All right? Now, why did we pick these formation reactions in particular? Well, because all the formation reactions of a ton of different compounds have been studied, and their thermodynamic variables have been tabulated. All right? And that's what this constants page that we had for this chapter. It's a big, ugly constants page. Okay? Let me just sort of look here. We have this compound. All right? And we have a delta H, a delta G, and an entropy value for that compound. All right? That is the enthalpy, free energy, and entropy change associated with the formation of this compound. All right? Now, luckily, we don't have to write it out and do Hess's law and sum up chemical equations, do that every single time. There's a way more convenient way that we can use these variables here because they all correspond to those formation reactions. All right? So what we're going to do is we're going to sort of prove that we can get the same information here. Whoops. Oh, that's pretty much it. Sure. By summing, I lied. I like to write it out. All right, we can get the delta G for a reaction. Okay, and let me just note, one of the things that I want you to have in your head, when we do equilibrium constants, when we build our equilibrium expressions, what do we remember? What over what? Products over reactants, great. So for this one here, for these equations, what I want you to remember is products minus reactants. All right, that's our little phrase that we're going to have. Products minus reactants. All right, so in order to get the delta G of my reaction, I'm going to take the delta G of my reactants, my products, and I'm going to subtract off the delta G of my reactants. Okay? But if we have more than one product or more than one reactant, we're going to have to sum them up. So I'm going to take the sum of the delta G of my products minus the sum of the delta G of my reactants. And I also have to multiply by my stoichiometric coefficients. All right, so we had this chemical equation, 2 NO2s going to our N2O4. All right, so we can go to our constants page here. We're going to have to look up those compounds. We can note that they're in alphabetical order based on the elements present. All right, so N2O4, I'm going to look under nitrogen, that first element. All right. We got to be careful here because I have two N2O4s. Which one am I going to use? The gas. And why that one? Because that's what was in my chemical equation, right? So you got to do the exact match from this table. Not everything has multiple states of matter, but some stuff does. And you got to make sure to grab the proper state of matter here. So I'm going to grab this entry. I think the other one's at the top of or the bottom of the previous page. So I'm just going to copy and paste this over. Go back and grab the next one, the last one. I think it's down here. There we go, NO2. Copy and paste this one. I'm going to try to clean this up a little bit. Okay, and I'm going to remind you from the previous page, our order of our compounds was the delta H, the delta G, and our entropy. It's important to note the units here. This is going to be especially important later on. The entropy and the enthalpy and the free energy are in kilojoules per mole, whereas entropy is in joules per mole Kelvin. Okay? So I want everybody to take a second. Let's calculate the delta G of this reaction using these standard values here. All right, using our equation, our products minus reactants multiplied by their stoichiometric coefficients. All right, my product, I'm talking about delta G, so I'm going to look at this middle column here. My product is that N2O4, so I'm going to grab that 99.8 kilojoules per mole, and I'm going to subtract off my reactants, my 51.3, but I'm going to multiply that by that stoichiometric coefficient, right, from my balanced chemical equation. So it's going to be minus 2 times 51.3 kilojoules per mole. All right, and if we punch that into our calculator, we get that same negative 2.8 kilojoules per mole value, letting us know that this reaction was spontaneous. All right. The nice thing is that this product minus reactant business doesn't just work for delta G, it works for all 3 of those thermodynamic variables. So I can figure out the delta S of my reaction by doing my products minus my reactants. Multiply, summed them all up, multiplied by their stoichiometric coefficients. Products minus reactants. Same with my delta H for my reaction. All right, sum up all my products minus my reactants. All right, so that means that not only can I figure out whether or not this reaction is going to happen, whether or not it's spontaneous or non-spontaneous, I can also determine whether or not this reaction is going to create order or disorder, and whether or not it's endothermic or exothermic. All right, so that's what we're going to do next. We're going to calculate our delta S and our delta H for this reaction. Before we do it, before we see what the numbers say, if we look carefully at this chemical equation, what would we predict our change in enthalpy to be? Does this reaction create order or disorder? All right, let's take a poll here. Who thinks we're creating order here? Who thinks it's disorder? Okay, so both of these sides have gases. So state of matter hugely plays into entropy. But that's a wash, right? There are gases on both sides. And we have on our left-hand side 2 individual gas molecules combining into one big one, right? So what's a more disordered state? 2 things floating around independently or one thing? I know that was an awesome little depiction right there, the flailing arms depiction. Anyways, yeah, so 2 things are going to be more disordered than when they combine together into one, right? We've created a more ordered state by joining those things together. All right. Yeah, so anyways, we're going to predict that our delta S here is going to be negative, or this is going to be an entropically unfavorable reaction. But now let's use our values here and prove it, all right? So I want everybody to do the analogous calculation of what we just did for our delta G to calculate the enthalpy and entropy change, all right? Or rather, I'm going to ask you guys to do delta S, and I'm going to work on delta H, all right? You can just trust me. Excuse me. All right, so products minus reactants, right? I take the entropy of that product, that 304.4, and I subtract the entropy value for my reactants, but I gotta multiply it by that stoichiometric coefficient. And we indeed get a negative number here, meaning that this reaction is entropically unfavorable. Right? Now, entropy we can predict by looking at our chemical equations, all right, sometimes. Enthalpy you don't get just by looking at your chemical equation, right? You couldn't really predict whether a reaction is endothermic or exothermic, at least not with more information. In this case, this reaction better be exothermic, which it is, because there's no other way to have a spontaneous reaction that's also entropically unfavorable. Right? It's got to be favorable from one standpoint. It can't both be endothermic and entropically unfavorable. Those are reactions that never occur. Right? So if this thing's going to occur, it's got to be exothermic as well, which we just proved with our thermodynamic variable calculation. All right? That negative 57.2 kilojoules per mole value. Cool? So bottom line is we have this tabulation here of all these different compounds. Right? And for all these different compounds, what's listed is the enthalpy, free energy, and entropy for that formation reaction. All right? So we can then combine these thermodynamic standards, these values here are called thermodynamic standards, together to get the entropy, enthalpy, and free energy of any reaction that we can dream of. And I know everybody's like, wow, that is the coolest thing I've ever heard of ever. Because if you can track down your products and reactants on this chart here, for any chemical reaction that you can come up with, you can predict whether or not that reaction is going to happen, right? Whether or not it's a spontaneous reaction. You can predict whether or not it's going to absorb or release heat, and whether or not it creates order or disorder, right? So for any reaction that you can dream up, as long as you can find those values on this table here, you can figure out those 3 thermodynamic variables. I know, super cool, all right? Now, I have been lying to you a little bit. It's a little bit more complicated of a story than that, because if we look carefully, we have these little knots here. So really what we calculated here is not just delta G, but we got to be good. It's delta G naught, delta S naught, and delta H naught. All right. And these little knots here, they mean something. All right. These here mean that we're talking about a reaction under a specific set of conditions, what we call standard conditions. And standard conditions is a specific set of conditions. Most notably, our temperature here is specifically going to be at room temperature here. All right, so we're talking about this reaction being, in this case, spontaneous and being exothermic, all at 25 degrees Celsius or 298 Kelvin. All right, so it was like, oh, cool, we can figure out whether a reaction is spontaneous or non-spontaneous. Okay, yes, but only at this specific temperature here. And all of a sudden it's like, well, crap, that seems pretty limited. Well, don't worry. We have a way of figuring out whether it's spontaneous or non-spontaneous at other temperatures as well. All right, so now we're going to talk about delta G at any temperature. Okay. So we had our equation, delta G equals delta H minus T delta S all right. The problem is that we can't utilize this value, for example, this 2.8 kilojoules per mole. It's really only good at that one temperature. Reaction free energy changes quite dramatically with temperature, right? So this value is really only good at that one temperature. Fortunately for us, though, the other two thermodynamic variables, these ones here, aren't as sensitive to temperature. So we can approximate our delta G at any temperature using this equation by using those standard values for enthalpy and entropy. Right? We get to plug in what we get from our constants page here and here, and then we'll just change our temperature in our equation to figure out what delta G is at any temperature. All right? So first of all, this reaction, let's just go back to our little cheat sheet that we made here. This reaction was an example of a reaction that was exothermic and entropically unfavorable, right? That means that this reaction would be spontaneous at low temperatures, but I can crank up the temperature enough where eventually that reaction is going to become non-spontaneous. All right, so we know that it's good at that 298 Kelvin, but now let's ask, okay, we're going to use, just for the sake of time, and we've already calculated, is this same reaction spontaneous at, and let's crank up the temperature. Not 298, let's go all the way to 350 Kelvin. All right, so we don't know our delta G at this temperature. That's what we're calculating. But what we're going to do is we're going to plug in that delta H naught value that we calculated. All right, our delta H naught value that we calculated was that negative 57.2. And I'm going to be good. This was kind of an annoying one, paying attention to sig figs here. I have to keep that bar on the 2. All right. This was my enthalpy, my standard enthalpy. We're going to subtract that temperature of 350 Kelvin. multiplied by that enthalpy, or rather entropy value of negative 175.8 joules per mole Kelvin. Joules per mole Kelvin, there it is. Okay, and this was my entropy value. But this is where we got to be careful, and we made note of those different units because I got a unit problem here. Why can't I combine these two terms? If I look carefully, my Kelvin's going to cancel out. But what's not going to cancel out here? Or what's not going to match? I got kilojoules over here and just joules over here. You can't combine units with addition and subtraction, or rather you can't combine values with addition and subtraction unless they have identical units, right? You can't add grams and milliliters. It doesn't work like that. So I got to make sure they match. So what I'm going to do is I'm going to take that entropy term and I'm going to divide it by 1,000 because there are 1,000 joules in 1 kilojoule. So that'll help square my units away to be in kilojoules. And there's my entropy term. All right, so my delta G at this temperature, at this elevated temperature here, is now positive 4.29 kilojoules per mole. So what will we say about this reaction at this temperature? Spontaneous or non-spontaneous? Now it's non-spontaneous, right? We raised Now we've raised our temperature enough that that entropy term takes over, and this reaction was entropically unfavorable. So now this reaction will no longer occur at this elevated temperature. All right, so if we want to get delta G at any temperature outside of standard conditions, what we're going to have to do is use our formula here, where we can plug in the standard enthalpy and the standard entropy in order to figure, and our new temperature, to figure out what our new delta G value will be. Okay? There's something else that we can kind of do here that's pretty cool. All right. So now we're going to discuss what are called phase changes. All right, substances have a characteristic melting point and boiling point. So let's take water, for example. What's water's boiling point? 100 degrees Celsius. What's water's melting point? 0 degrees, right? Or other freezing point if we're thinking about it going that direction. Yeah, so we have these characters, and we could do that for any substance, right? We can define its melting point and its boiling point. All right, importantly, at these temperatures, all right, so at a melting or boiling point, all right, the delta G of that phase change is equal to 0. All right, so let's take water, for example. Water goes from liquid to a gas. All right, this would be the boiling of water, right? Going from that liquid phase to that gaseous phase. okay? If we were at our boiling point, the delta G of this reaction would be equal to 0. All right, that's what it means to be at that boiling point, right? This reaction no longer has a preference for one side or the other, right? These two phases are in equilibrium with one another is another way to say that. Let's actually say that. Okay, our two phases are at equilibrium. This reaction's no longer going forward, no longer going backward. Okay? So that means that we can use, and so now we know what the delta G is at that particular temperature. It means that we can use this equation here to approximate our melting point. Now we know what it is for water, so this isn't going to be the most interesting calculation in the world. But there's a ton of other compounds out there where we don't know what its melting point is. We don't know what its boiling point is, and we get to use this strategy to figure out to calculate what those values are. All right, so let's do it for water here. We're going to take this equation, our any temp equation, all right? And what we're going to do is we're going to set that delta G equal to 0. And now what we're interested in is that temperature at which this reaction occurs, at which this phase change, rather, not really a reaction, but a phase change, is going to be at equilibrium. All right, so let's rearrange. I want everybody to take a second. Rearrange this equation and solve it for T. All right, so our boiling point temperature here, I'll mark it TB. We can calculate that by dividing our standard enthalpy by our standard entropy. All right, so let's go ahead and do a sample calculation here for water. We're going to need to first calculate what that enthalpy change is, what that enthalpy change is and what that entropy change is using that equation that we were talking about earlier, right? Products minus reactants. Where was it? Products minus reactants, using this guy here, okay? All right, cool. So I'm going to pull up that data, and let's just note here, our product is the gas phase water. Our reactant is that liquid phase water. So now I got to go to my table and look these up. Element of P. Here we go. All right. Remember, the first column is the enthalpy. The middle column's the delta G, but I don't care about standard conditions. So I'm going to look at the first and the last column here. All right, I'll tell you what, we'll make a deal. How about you all calculate the delta H naught, and I'll go ahead and calculate the delta S naught, and we'll combine powers here. All right? All right, remember, products minus reactants. All right, what do we get for our delta H? Whoops. Somebody, anybody, what's delta H? 44. Now, we got to be careful here. Because this was an addition, or rather a subtraction problem, we really got to make sure to pay attention to where our sig fig is. So really we're going to be good and say 44.0. All right, and I'll tell you that the delta S that I calculated was 118.8. That was joules per mole Kelvin. All right, we're going to approximate that boiling point. That's our 44.0. All right, and what problem am I going to run into here? The whole joule kilojoule business again, right? I got to make sure my units square away so that they actually cancel out. So again, I'm going to have to take that denominator and divide it by the fact that there are 1,000 joules in 1 kilojoule. All right, and I'm going to put this in parentheses to make sure that it stays on the bottom when I punch it into my calculator. All right, when we punch this into our calculator, we get 370.4. And what are my units? Kelvin, right? So my joule canceled out, my kilojoules cancel out, moles cancel out, and I'm left with my 1/1 Kelvin, or just Kelvin. All right, but of course we don't really think very much in Kelvin, so let's go ahead and convert that. We're going to subtract off that magic 273.15 number. All right, and we get our TB of 97.2 degrees Celsius. Is that the boiling point of water? Not quite. All right, look, we said that delta H and delta S don't change very much with temperature, but they're still not exactly the same value. So this is only an approximation here. But that gets us pretty freaking close to the actual value of the boiling point of water, right? So that's a pretty useful, even though it's just an approximation, it's still a pretty useful tool here for exploring phase changes just based on tabulated data, right? So again, water might not be that interesting, but there's plenty of compounds that you don't have an intuitive sense about, and you can approximate what their boiling point is using this method here, where we took our any temperature equation, and we said that since this is at this phase change temperature, delta G is equal to 0, and we just rearranged to solve for what that temperature was. Cool. All right. Another thing we're going to talk about here. We're talking about delta G, right, which is telling us whether or not the reaction occurs. We already had this measure that we were using for whether or not a reaction proceeded in the forward or reverse direction. We even looked at this value and said, oh, this reaction strongly favors the product, or this reaction weakly favors the reactant. What were we looking at there? Okay, our equilibrium constant, all right? Turns out that there's an intimate relationship between the delta G of a reaction and that equilibrium constant, all right? So now we're going to look at the relationship between delta G and KEQ. All right. It turns out that the equilibrium constant is equal to E, that magic number that comes out of our calculus, to the negative delta G naught over RT. you can convince yourself that if you plugged in a negative value for delta G, that would make KEQ a positive number, right? Because you're multiplying it by negative delta G, so that would become positive, right? And likewise, if delta G was positive or non-spontaneous, that would give you a KEQ less than 1, okay? So there's this intimate relationship here. We're going to note that the ideal gas constant, from our constants page, but nonetheless, 8.3144 joules per mole Kelvin. And our temperature here, since this only really works for delta G naught, is that 298 Kelvin. All right, well, we already studied one of these reactions. Let's grab one of these reactions that we studied previously. All right, we'll do our dinitrogen, our NO2 to N2O4. Okay. We had calculated that the delta G naught for this reaction is equal to negative 2.8 kilojoules per mole. All right, so then let's plug this information into this equation and figure out what our equilibrium constant is for this reaction. All right, and I'm going to be good and make a point and put in all my units as well. So my KEQ is E to the negative delta G, so negative 2.8 kilojoules per mole, divided by R, that 8.3144 joules per mole Kelvin, multiplied by T, our 298 Kelvin. I said I was going to be good and put in our units because if we look carefully, what problem are we going to have? This friggin' joules, kilojoules business, all right? It's just how these values are tabulated. They pick one set of units, so we just got to be careful and look out. So we're going to then multiply by the fact that 1 kilojoule, again, divide by 1,000, right? To convert to kilojoules. You could also convert the numerator here into joules if you wanted. It doesn't really matter. But you got to make sure those units square away. That's the bottom line. All right, and now everybody's going to take a second, find that E button on their calculator. Okay, we're going to note because we're dividing by this big long term here, we're going to make sure to put it in parentheses when we're going to divide by it, right? Make sure it stays in that numerator or in that denominator. Right? So we punch this into our calculator. We get 3.1, a value that's over 1 but less than 1,000. So this would be a reaction that weakly favors the products. What's up?
Are there any units?
There are not units for, rather we're going to gloss over our units for equilibrium constants. You can note that everything indeed did cancel out here. Cool. All right, so last thing that we got to cover here. I lied to you yet again. All right, we talked about how standard conditions were these limited set of conditions where our temperature was specifically equal to that 298 Kelvin, right? Room temperature, there we go. All right, standard conditions. That's what that knot was these standard conditions. It turns out that standard conditions is even more stringent than that. Not only does it dictate what temperature it's at, it also means that your concentration of every species is at 1 molar, or the pressure of any gas is at 1 atm. Right? So it's saying that this reaction will indeed spontaneously proceed in this forward direction here if we're at 298 Kelvin and if we have 1 atm of each of these gases in that reaction mixture. Right? So it's actually a pretty limited set of whether or not this reaction will occur. It's not saying it will always occur. It's saying that it will occur under this specific set of conditions. And it's like, oh crap, well then that's super limited. What if I wanted to do any other set of conditions? We talked about doing any other temperature, but like I don't want to have to start my reaction with 1 atm of each of these gases, right? So then how would we figure it out if we were any other conditions? Don't worry, we have a way to do it. Okay, so last thing we got to cover here is delta G under any conditions. All right, and again, we're going to kind of like tug at that relationship between delta G and our equilibrium constant K. Back when we were studying equilibrium constants, we also had this quantity that we introduced, and we said that if we calculated that, we could compare it to our equilibrium constant, and that would tell us whether or not our reaction was going to go forward or backwards. That was called our reaction quotient. Our reaction quotient, and we used that variable Q. Our reaction quotient was just that same equilibrium expression, but we plugged in non-equilibrium values. All right, equilibrium expression, meaning our products over reactants. So we're going to utilize this reaction quotient here. We can get the delta G of a reaction under any conditions using this equation here, where we're going to take our delta G of our standard conditions, under standard conditions, delta G naught, all right, and we're going to add RT natural log of that reaction quotient Q. So this is how we're going to plug in those any conditions, right? Because we can plug in any conditions in order to get our reaction quotient. And so this is then how that's going to factor, those any conditions factor in to our delta G calculation. Okay, since we've been beating this one to death, let's just stick with it here. We're going to take our 2NO2, gets us to N2O4. And as we noted, the delta G naught of this reaction was that negative 2.8 kilojoules per mole. So we know that this reaction will proceed spontaneously in the forward direction if this gas was at 1 atm and this gas was at 1 atm, right? Because that was our standard conditions, okay? So now we're going to ask, is the reaction still spontaneous if the pressure of that product is, let's say, 5 atm, and the pressure of that reactant is 0.5 atm. All right, so yes, this reaction will occur if both of these gases are at a pressure of 1 atm, but it quickly stops being at 1 atm, right? If that reaction actually occurs, that means my reactants are going to decrease, my products are going to increase. So let's say, okay, after this reaction's run for a little bit, my reactants have decreased, my products have decreased. Is this reaction still going to go in that forward direction? All right, so first step is everybody's going to take a second and build me that reaction quotient Q. All right, again, your reaction quotient is just your equilibrium expression, which means it's what over what? Products over reactants, right? Same thing as our equilibrium expression. It's just that now we get to plug in any value we want. Right, my product is that N2O4, my reactant is that nitrogen dioxide, and I'm also going to have to remember to do what? Why is this wrong? We're not quite done yet. Products over reactants, but what's the other thing I got to remember to do for my balanced chemical equation? Exponent, right? My coefficients become exponents. So I got to square that pressure of my reactant. Cool. All right, well then let's calculate what Q is. This is going to equal 5 divided by that 0.5, and I'm going to get a little bit lazy and just for the sake of not confusing, not include my units here. But I got to square that 0.5. So my value for Q here is 20. All right. So now we're going to use our equation. We're trying to figure out what this delta G is under any conditions. We got to use that negative 2.8 kilojoules per mole. That was what we got for our standard free energy change, right? Our delta G naught. Then we got to add R, that 8.3144. Joules per mole Kelvin. Times our temperature, our 298 Kelvin. I didn't leave myself enough room. Times the natural log of that value for Q, which we calculated to be 20. We have another similar problem here. We're not going to be able to combine these two terms because of what? The friggin' joule, kilojoule thing. All right, so anytime we use R, you basically want to get in the habit of converting it into kilojoules by dividing it by 1,000. All right, but now we can combine them. Oh, okay, my bad. I wrote it right and punched it wrong. Cool. All right, we punch all this into our calculator. We get a value of 4.6 kilojoules per mole. So under these conditions, is this reaction spontaneous or non-spontaneous? Now it's not going to happen anymore, right? My reactants have decreased too much. This reaction will be non-spontaneous, which really means that if I were to combine 0.5 ATMs of nitrogen dioxide and 5 ATMs of our product here, this reaction would not go spontaneously in the forward direction, but would rather go in the reverse direction in order to reach equilibrium, right? Non-spontaneous, meaning it's spontaneous in the reverse direction. Cool. All right, so basically, you spent all last class period building this equation here, building this equation here, and we learned how to use it today. Okay? We learned that we can grab those values, those standard enthalpy and entropy and free energy values from that table and combine them to figure out whether any reaction is spontaneous or non-spontaneous under those standard conditions. Standard conditions is pretty limited though. So then we also talked about strategies for figuring out if we were using a different temperature or if we were using any other set of conditions other than those standard conditions, how would we go about finding that information? Cool, what's up?
Is our test still on Monday, Tuesday?
No, it's Wednesday. Okay, yeah, real quick. Your exam is Wednesday, Thursday, the 8th and the 9th, I want to say. Yeah, okay. So basically, what that means is that we'll have a review session on Tuesday. On Thursday, I'm going to have to start in on new material. If you need to use the class time to take your exam, you can do so. I won't be taking attendance. There won't be a daily quiz, but I will cover new stuff, so you'll have to watch a video if you missed class. Cool. All right, enjoy your break.